You're listening to Explain This.
Our new podcast from The Brink explores big and small pictures of research done at Boston University, from microbiology to art history and everything in between. Join us as we interview on-campus experts who break down areas of study and put their work into real-world contexts.
All stars formed with protoplanetary disks. So the potential is there for all stars to have planets. And when people look for exoplanets, which is planets outside of our solar system, they find that most stars have planets. So it seems that planet formation is a very efficient process. It's just about figuring out how exactly do we get to the planets.
Billions of years ago, the sun was a young star just in its infancy, swirling through a dense cloud of dust and gas. Scientists aren't entirely sure how, but eventually it grew into the familiar bright ball of hydrogen and helium at the center of our solar system. These dense clouds of dust and gas are called protoplanetary disks, and essentially they feed growing stars and accumulate into planets. Scientists look at protoplanetary disks in the galaxy to learn about the early stages of planet and star formations, which can then provide clues about the early years of the sun and the Earth. Catherine Espaillat, director of BU's Institute for Astrophysical Research, studies the formation of planets and young stars by observing them in the wild with multi-wavelength, high-powered telescopes and computer modeling. I'm Jessica Calarasi, science writer for BU, and today we're talking about the formation of planets in our solar system and elsewhere in the cosmos. Catherine, thank you so much for being here.
My pleasure. No, I love any chance to talk about baby stars.
Great. That's what we like to hear. Can you start by walking us through what a protoplanetary disk is and how planets form within them?
Yeah, so we think that planets form around young baby stars. So young stars, and our sun went through a phase like this too when it was a baby star. Stars form out of clouds. So if you look at our own solar system, you can see evidence that there was a protoplanetary disk around the sun. And that's because if you look at our solar system edge on, you'd see that all the planets line up around it kind of looks like they come out of they're all aligned on a plane that comes out of the equator of the sun. So it gives you an idea that there was something flat that they were in, like kind of like a pancake that like the sun was in the center of. And out of that, gas and dust that was in that protoplanetary disk that you can think of as a pancake, that's where the planets grew out of. Also, the evidence that we have that there was a protoplanetary disk is that there's an asteroid belt between Mars and Jupiter. And this is all leftover dust particles and large boulders and large rocks that didn't make it into planets. So they're leftovers. Another piece of evidence is that if you look at our solar system, you see that the rocky planets, the planets closest to the sun are rocky, and the ones furthest away are gaseous. And that's because the temperature as you get further away from the sun goes down. So the further away you get from the sun, the colder it is, and so you can have ice. And ice is actually very sticky out in space. So the ice helped them stick together and they got bigger and bigger, bigger. And actually the cores of the giant planets are Earth size. And so then those cores of those planets that formed in the outer part of the solar system, they were so massive that they were able to attract the gas that was in the outer part of the solar system. So that's why we have gas giant planets. In the inner part of the solar system, there wasn't ice. So the biggest you could get was something like Earth size. So it couldn't get much bigger than that. So those are the most obvious pieces of evidence that our own solar system formed out of a protoplanetary disk. Something that would really blow your mind is that so if we go back all the way back to the Big Bang, the only elements that existed in the universe at the time that it was created was hydrogen and helium. Most of the elements heavier than that formed out of stars. So the very first stars in our universe were made up of hydrogen and helium. And then as they were living their lives and they were burning their fuel, they converted the hydrogen and helium into the heavier elements. And then some of those stars went supernova, they exploded. And because of the energy in those supernova explosions, they formed the heaviest elements. And then those elements went into seeding nearby molecular clouds, which is where baby stars form out of. So we're all part of this cosmic cycle where the fact that we have rocky planets, that we have Earth, it's because all of that material was made in previous generations of stars that died, and then their heavy elements were spread out throughout their nearby galaxies because there was only hydrogen and helium at the time of the Big Bang.
Right. So how do we get from only that, those two elements, to a full-blown planet?
Yeah. So it all comes down to starting with very small things and then building up very big. So to give you an idea, in these protoplanetary disks, most of the particles are less than the width of a human hair. Now, because of, I mentioned some ice, if things are cold, they get a coating of ice, they get stickier, then they coagulate, which is just a fancy word for saying they stick together and they get bigger and bigger. It's still a question, what's the initial composition of the protoplanetary disk? And that's something I'm very interested in, especially with the James Webb Space Telescope, because the data from the James Webb Space Telescope, JWST, that's going to give us access to the molecular composition of protoplanetary disks, right? Because unlike life on Earth, we need molecules, right? We need water. And so we need to figure out, where did this water come from? So with JWST, we'll be able to look at protoplanetary disks, take data, and be able to measure how much water is in these systems to help us start to piece together many more of the details about how do you end up with a watery planet like Earth, right? Because all of the other planets in our solar system don't have water like Earth.
That's so interesting. Can you tell us more about how you're using JWST in your research?
With JWST, I'm still looking at our galaxy. All my science is galactic science because we just don't have even JWST isn't large enough to look at star formation, planet formation in galaxies that are very far away. So I'm looking in our galaxy nearby, and in addition to looking at the molecular composition of protoplanetary disks, something that I'm really interested in right now that I just published on paper on is looking at the connection between the star and the disk, right? Because the disk surrounds the star is which creating the energy and the power. And these young baby stars are very variable, which means they're constantly flickering, they're getting brighter and fainter. And so that means that the energy that's shining on planets and the protoplanetary disk is also changing, right? So here on Earth, our sun is very stable. That's why there's life on Earth. It's not constantly changing, right? Because life likes to have a certain amount of energy and be able to count on it. But for these young stars, I'm really interested in figuring out, when the star is changing its energy output, what is the effect that we see on the protoplanetary disk?
So I'm curious, do planets and stars form at the same time?
So one of the big discoveries I made earlier in my career was identifying the first protoplanetary disks that had gaps, where they had the star, some material, a gap, and then more material. And then more recently, there have been many more gaps detected in protoplanetary disks, and some of them very small. These gaps were found in protoplanetary disks that are considered to be a bit older, so like 1 million years old, which is still like really young on a star lifetime. Now we're finding gaps possibly in the even earlier stages when stars are even younger. So that's why we think maybe it's possible that planets are forming at the same time that the star itself is forming.
So since baby stars are forming all over the galaxy, it seems like this is very common. How do you decide where to zoom in and study?
So stars are forming predominantly in the spiral arms of our galaxies. And then I focus on the stars that are closest to us, just because that means they appear brighter to us, and that means it's easier to collect data for them. And then out of those stars, because those are thousands of stars, tens of thousands of stars, I focus on the ones that are the analogs of our sun. My interest originated with trying to understand the solar system and how our planets came about. So I'm most interested in those stars that most resemble what our sun was like when it was a baby star. So those are the ones that I focus in on. So I look at the solar analogs that still have protoplanetary disks. And I spend a lot of my time looking at the ones that have gaps, because I think that those are the ones that are most promising for eventual detection of planets once our instrumentation gets good enough to image these planets and disks.
Oh, so are there some protoplanetary disks that don't ever develop planets?
The way I frame that is all stars formed with protoplanetary disks. So the potential is there for all stars to have planets. And when people look for exoplanets, which is planets outside of our solar system, they find that most stars have planets. So it seems that planet formation is a very efficient process. It's just about figuring out how exactly do we get to the planets. So it seems like lots of planets are formed, but how exactly do we get there?
How do moons factor in? Are moons formed from the same disks?
Yes, they are. So it depends on the moon. So for the gas giant planets, when they form, they have their own mini disk. So you have the star with protoplanetary disk, and then within the protoplanetary disk, you have the gas giant planet, and it has its own disk around it. And then out of that mini disk, you can think of it as a protolunar disk. Then the moons form out of that protolunar disk. So for example, like Jupiter, Saturn, Uranus, Neptune, they have a bunch of moons, and that's because they had their own protolunar disks that surrounded them. That's why Saturn has rings. Saturn's rings are the leftovers of its protolunar disk, and actually all the gas giants have some ring around them if you look at it long enough. None of the terrestrial planets, the inner rocky planets, are massive enough to have their own protolunar disk. That's only the gas giant planets that are big enough they get enough gravity that they can assemble more material around themselves. So then the moons for the terrestrial planets have to come from somewhere. So either they're captured, like we think Mars captured its moons from the asteroid belt, or there was some kind of like collision that led to the creation of a moon, like we think for our own moon.
Okay. So how old are the baby stars that you study?
These young stars, the ones that I study, the baby stars, they're between 1 and 10 million years old. Like 10 million years old is considered old for these baby stars. Yeah. 1 is like, they're like nice and, cute and young. But yeah, that's a typical age range. Like 1 to 10 million years is the time scale that we give for a baby star.
And is that the same for the young planets too?
Yeah. The planets are about the same age as the star. So the Earth is about the same age as the sun, just a little bit younger.
Right. Can you tell us too how you became interested in studying astronomy?
Yeah, well, actually, my interest in astronomy started when I was really young. So like a preteen to teenage years, like I watched a lot of PBS and like Nova TV specials about everything out there. And so I was really interested in our solar system and how it formed. But I wanted to be a doctor because I thought astronomy would be like my hobby. I'd be a stargazer. So I went to college, as a pre-med, and then I took an astronomy class. I was like, oh, wow, this can actually be like a job and a profession. So then I decided to just switch over to an astronomy major. So then when I started grad school, I studied what are called active galactic nuclei, which are supermassive black holes in the centers of other galaxies. And then I eventually made it back to planet formation. So it kind of eventually found my way back to my original passion, which is planets and then trying to understand how they form.
Right. And so why is it important that we study protoplanetary disks?
Yeah. So if we want to understand, where do we come from? This is one small way to get at answering that question. So where do we come from? Where does Earth come from? Where does our solar system come from? And the answer to that is these baby stars that are surrounded by protoplanetary disks. That's where the planets form out of. And then in particular, baby stars that are what our sun looked like when it was a baby star. It's important to study protoplanetary disks because that's where planets form out of. So if you want to understand where Earth formed from, we have to look at protoplanetary disks. And in particular, we want to look at the protoplanetary disks around solar analogs. So what did our sun look like when it was a baby star?
Wow. I feel like I learned so much. Thank you so much for being here, Catherine.
Thank you, guys.
Explain This is a podcast produced by The Brink at Boston University. This episode was mixed by Andrew Halleck and edited by Sophie Yaren. To learn more about us, go to bu.edu/brink.
Stay curious out there, folks. We'll see you next time.